Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will kind of consider the solution of the magnetic vector potential, the wave equation for the magnetic vector potential, and then see how it can be used to obtain the far fields or the radiation fields of the most elementary form of an antenna system, okay, or an antenna as such. I hope you remember this wave equation that we derived in the previous class or the previous lecture, where on this side, on the left hand side, you see the familiar wave equation, but on the right hand side you do not really see the term that is usually there in the wave equation, because in the plane wave for electric field E, this right hand term was actually equal to 0, but you now know that you cannot actually have you cannot generate waves without any source, and actually this wave equation is the one that actually has or the wave equation for A contains the term which actually generates the electromagnetic wave, okay, and that term is the current distribution mu naught into J. First of all, does this equation make sense? So you can try for example what happens when the frequency goes off to 0, that is under the so called static condition, del by del t or del square by del t square terms go to 0, then del square A will then be equal to minus mu naught J, which is precisely the equation that we obtained similar to Poisson's equation for the magnetic vector potential, okay. So this equation does make sense, at least in the case of DC conditions or when the time variation is not present or in the so called static condition. But we know that the current distribution need not be always static, and it cannot be always static or it cannot be static if we want to have some electromagnetic waves generated by the antenna. So in that case, when J term, the current distribution term, varies both as space as well as with respect to time, what should happen to the wave equation A, or what should happen to the solutions or type of the solutions for the vector potential A. And in order to arrive at this actually is a little bit of a complicated stuff, okay. So we won't really take the complicated approach, we will do a lot of approximations, or as I would like to call it, as a lot of hand waving. So don't worry too much if you don't follow the following analysis, but these are really brought about by a little bit of a hindsight after knowing what the final result should be and the kind of approximations that we make leading towards the final solution, okay. This is just to show you the kind of physical insights that go behind the analysis. A proper rigorous analysis is not what we are aiming for, okay. Having made that statement, let us go back and see what kind of a solution that we are looking for, okay. Because we will be dealing with radiation and antenna fields, we will be working mostly with the spherical coordinate system. So we want our solutions to be solved in the spherical coordinate system. That is the first thing that we want to do. Second is, this is a wave equation, and with the wave equation comes the question of phase delay, waves which are propagating in a given direction, waves which are getting reflected from some other direction. So at any given direction you have both a forward going wave and a backward traveling wave. So all type of solutions which are of the form f of t minus u by, or z by u in the case of a transmission line, should kind of be valid over here as well, okay. And it is in fact true, the solutions of this one are no more difficult, at least in principle, than the wave equation solutions that we have looked for, okay, except that our life is little more complicated. The vector quantities are being involved, not the scalar quantities. So there on the transmission line it was the voltage which was involved, but here you have a vector quantity which is the vector potential that is involved. But we will analyze this equation only for a single component. Let us say that component is Ax, and of course to generate Ax you do not need Iz or Iy, that is the current elements along Z or Y, you do not need those elements, because the direction of J is the same as the direction of A, okay. So as long as you remember this, then you know that to generate the component Ax you need some current distribution Ix, okay. So this is the current distribution that you want, okay. With these two things in mind, let us rewrite this del square A, okay, in the spherical coordinates, and we will assume that we have a function purely as a function of r and t. We want a solution which is independent of phi, and independent of theta. As I said, this is not the most general solution that is possible, but this kind of leads us to the type of fields that we are going to see, or to the type of solutions that we will see in the usual radiation fields. Okay. So, you can rewrite this del square in the spherical coordinate system, and it turns out to be something like this. So, 1 by r square del by del r, okay, times r square del Ax by del r. Remember, we are only considering the component Ax, okay. So, minus mu naught epsilon naught del square Ax by del t square must be equal to minus mu naught Ix, okay. Please remember that we are considering only one particular component, and therefore, this equation that we have obtained has now become a scalar equation rather than a vector, okay. We now postulate the solution. So, this is our postulate, okay. This is the kind of hand waving that I am going to do now, okay. So, this Ax is assumed to be of the solution some f of r t divided by r. There is a nice reason why we put this 1 by r over here, okay, because with this kind of a solution, as you will see, the fields will fall off as 1 by r and the power density will fall off as 1 by r square, okay, and that is an important part for radiations, as you will see in this hopefully, or in the next module as we will discuss, okay. For now, the solution Ax, which is a function of r and t, can be expressed in terms of some arbitrary scalar function f of the components r and t divided by r. So, this is sometimes called as the spherical wave, okay, and you can substitute this expression into the expression for del square Ax term, okay, and I will not actually carry out those substitutions. You can actually do that one. There are a few terms which will be double differentiated with respect to r, then there will be a double differentiation with respect to time, and some of those terms actually cancel out each other, so that you obtain this next equation, which is del square f of r t by del r square minus 1 by c square, where I have identified c to be 1 by square root of mu naught epsilon naught. I am sure you agree with me on this one. Mu naught and epsilon naught are the permeability and permittivity, whose product and 1 by square root of that product is actually equal to the speed of light, okay. So, I have replaced that mu naught epsilon naught by 1 by c square in this expression. So, I have minus 1 by c square del square f of r t by del t square, okay. This would then be equal to 0. Why is this equal to 0? Because I am looking for solutions not on the current distribution itself, okay. There is a technical difficulty involved in that, therefore, we will not look at solutions right at r equal to 0, which is where we have assumed that the current distribution is located. So, solutions at a far away region, okay, from the current distribution Ix, which has been kept at r equal to 0. So, we will come back to that one, but right now we are looking at the solution far away from this. And what is the solution of this equation? Well, we have seen this one in the case of a wave equation on a transmission line with the voltage V in place of F, and in place of R we had Z, and in place of T we of course had T itself, and the solutions were like V plus T minus Z by U and V minus T plus Z by U, and we identified this one with the forward going wave and this one with a backward travelling wave, correct. V plus and V minus were the type of functions that you were considering, and U was the phase velocity. In this case, in place of Z you will have R, in place of U you will have C, okay. So, the solutions will be of the form F plus T minus R by C. I claim that there won't be any solutions of the form F minus T plus R by C. Why don't this solution exist? Well, this solution F plus T minus R by C moves away from the current distribution. Suppose this is the current distribution that I have kept, then this solution is actually F plus. It is a wave which is radiating away from the antenna, whereas F minus would be a wave that is incoming towards the antenna, and because we have not kept any other antenna in this entire universe, this solution is not acceptable, okay. So, we will not consider that solution. This solution is acceptable to us, so we retain this solution, okay. You should understand that the appearance of C is a very important thing. For example, you take this current distribution over here, okay, and then shake the current distribution a little bit over there, and then if you are looking at a point, let us say you are on moon, okay, you are on moon, and then someone on earth takes the current distribution along Ix and then just shakes it up. Okay. So there is a change in the current, right, Ix as a function of time, that should now get reflected. But what time should elapse before you sitting on moon or standing on moon would be able to see this? It will take some amount of time which is equal to the propagation delay time, right. The change in the the change in the current distribution has to show up after time elapse or time lapse of some L by C, where L is the distance between earth and moon. Okay. Or this is of course the reason why stars that have been shining that you would see today actually were shining some millions and billions of years ago, and this millions and billions of years actually represent the time lag between when the star emitted light and when you are actually looking at the stars themselves. So this is a very important aspect which we have which we have said the same thing when we discuss transmission lines, but I think it is an important point to note that influences or changes are traveling at a speed of light, and that is the maximum speed with which any information, any change in the physical system can actually change and be visible. Okay. So I have the solutions of the form f plus of t minus r by c, but I still do not know what the form of the solution f plus itself. Okay. So what is this f plus solution? Well, we will do something. We will try to go to the case where r goes to 0, that is we now try to approach close and close to the antenna. So as I approach close and close to the antenna, then what happens? I also reduce the time delay between what is happening at the antenna and when am I seeing that change. Okay. So if the current is now shaking like this, as I go near and near, I will immediately see. So if I am there at 1 kilometer from the antenna, I see it much earlier than I was at say 10 kilometer from the antenna. So as I move closer to r, closer to 0, this propagation delay time r by c moves off to 0 or goes off to 0, and the function simply becomes f plus of t. So what happens to Ax now? To Ax, as r approaches 0, means that the solution becomes f plus of t by r. Okay. So this would be the solution. Of course, this is a condition that r is going off to 0. So this is a very important condition, and since r goes off to 0 and this r is in the denominator, there is a good chance that this might actually blow up. Okay. Unless something else actually happens. But as we go closer and closer to r going off to 0, what will happen to the line integral that you had? So instead of a triple integral, of course you just have considered the line integral Ix, right. So you had Ix, and this was supposed to be how it was changing with respect to the source point and time. So there is a mu naught by 4 pi as well, and this was the capital R over dx, because this is the current distribution that is happening, and we assume that the current element is so small that this Ix r prime of t dx can actually be rewritten or can be simply factored out and written as mu naught Ix of t dx divided by 4 pi r. Okay. If you forget about what is happening to the left hand side and look at only on the right hand side, this is precisely the vector potential component Ax. Okay. As we go closer and closer, and in the so called quasi-static approximation, what has happened is there is no dependence on r, because the antenna looks same at every point. Okay. So this is kind of the solution that you would expect as you go closer and closer enough to the antenna. Okay. Again, this is not very rigorous, but this is kind of plausible arguments that we are making. Now you can see on both sides that r is in the denominator, which allows you to cancel it off from that and write f plus of t as mu naught Ix of t dx divided by 4 pi. So what we say is that the function f of t that we were looking for actually has the same distribution as the current itself. Current shakes, f plus shakes, right. But these changes are happening, or this change or this shaking thing and then observing this particular shaking of the current is happening only when you are very close to the antenna. Otherwise, if you are slightly away from the antenna, this part which is shaking will appear at a slightly later time than the part which is appearing at this point. Okay. So please remember this. Okay. So only when you are technically in the limit of 0 distance from the antenna that everything looks the same. Okay. And of course you are assuming that this antenna itself is a point like scenario, right. So this is not, the current itself is uniform, which means all points are themselves small and all points carry the same amount of current distribution. In that case, f plus is the same as Ix, but my solution at any distance r from the transmission, sorry, from the from the antenna is actually given by f plus of t minus r by c divided by r. So this solution will actually be given by mu naught Ix of t minus r by c dx divided by r. Okay. For a elementary dipole or a short extremely small antenna or a short antenna, the current that was appearing at r by c times earlier, right, would then give rise to the field now. So shake current now and here, right, some origin time, C shaking of current later there, right. So this is the delay effect that we were talking about. Of course, this we have assumed that the current distribution over the entire antenna element is the same, but what if the current element is not the same? So what if the element looks like this? Then what you have to see is that over this patch, which would be having a source distribution of r prime or the source point of r prime, then the current that you are looking at would also be different. This would be t minus r prime divided by c, because this would be the distance. So if this is your origin, this would be r, and this red line will be the distance from the field point, right. So sorry, from the source point to the field point, which is r minus r prime. Okay. So it is this distance which is important, from the source to the observation point. So this is the observation point, not from the origin to the observation point. Okay. So in that case, I can rewrite this as Ix of t minus r prime by c, of course how it actually varies with respect to r prime, and in place of Ix you can also write this as Jx, provided you have a volumetric charge distribution and not a linear current type of a distribution. So putting up all together, what we have is the magnetic vector potential at any observation point and varying with time is given by integral of mu naught I, which is the direction in which we have considered the current element, and how it is varying at the source point r prime, but the time delay that you are looking at, the actual distribution must not be evaluated now, it must be evaluated t minus r by c times earlier. Okay. So t minus r prime by c earlier is when you have to evaluate this. Okay. And dl prime denotes the vector element divided by 4 pi r minus r prime magnitude, which is the distance from the source point to the field point. Okay. This was for the thin line elements, but for the case of your volumetric distributions, you can replace this I by J. Again, the current distribution cannot be evaluated now, it must be evaluated at a time which is t minus r prime by c, that is some time t r minus r prime by c times earlier. Okay. And this would be the volume distribution divided by 4 pi r minus r prime. Indeed, this t minus r prime by c is usually denoted by Tr, and this Tr is called as retarded time. Okay. And this potential is actually called as a retarded potential. Okay. You can, instead of thinking of this loaded word called retarded, you can simply think of this as delayed potential. So the potential actually depends on the current distribution that has been there some r by c times earlier, not actually the time now, and this delay effect is incorporated by the delayed time, which we are denoting by T capital R. Okay. Let us quickly look at an example. Suppose I have a current, okay, element which goes all the way to infinity, but it starts at z equal to a. So there is a current element lined up along the z axis which goes from z equal to a all the way up to infinity. Okay. And we feed this current element with some current source. Let us say we feed it with a current source which will be turned on right at t equal to 0. So before that there is no current. Okay. And then this is kept at this one. Okay. Now I wish to find what is the field A at z equal to 0. So my observation point is actually at z equal to 0. Okay. How do I find this potential? Well, go back and write down the expression. I know that A will be along the z direction. Okay. So, luckily I do not have to write down what would be the direction. So, I know that A will be along the z direction itself, but I am evaluating this A at 0, that is at z equal to 0 is my observation point and a function of time. So, this must be equal to, since this is an integral over the line element, there is no volumetric integral. So, we can simply use this first form of the expression. So, that would be mu naught by 4 pi. What is the distance between r minus r minus r prime? R of course is 0. So, r prime is the source point. Source point is any point on this particular current element, right, which would be z prime. So, 4 pi z prime, and this is the current that I need to know. What is the current? Current was I0 u of t minus z prime by c, correct. This is just a function t minus r prime by c. So, instead of that we now have t minus z prime by c. The current is uniform along z. So, there is no dependence on z prime as such, integrated over dz prime. Now, this is mathematical equation, but let us look at this equation a little bit. Okay. What should be the limits of this integral? Should this limit be from a to infinity? Well, no. There is an important reason why it cannot be, because look at the step function. When will the step function be equal to 1 or will be non-zero? It would be equal to 1 when x is greater than 0. It would be 0 when x is less than 0, correct. Now, suppose the current is turned on right at t equal to 0, right, as per the unit step function. Will I be able to immediately sense this current through the current element which is kept at z equal to a? Will this be immediately visible to me? No, that won't be immediately visible to me, because we have to spend some time for these waves to actually travel, this disturbance to travel and reach the observation point, and it does so after a time lapse of a by c, correct. Thus, for time less than a by c, the potential A will actually be equal to 0. So, this is an important thing. So, unless you have a minimum time of a by c, this would be equal to 0. Now, can I, once let us say t is greater than a by c, now the bottom end of the wire is now kind of visible to me in some sense, then can I now go and write down the upper integral limit as from that point to the infinity point, a to infinity? No, again u of x or u of t minus z prime by c will be positive as long as t minus z prime by c is greater than 0, correct, which means that for some t which we will call as capital T, no, if I fix this capital T, okay, some time that I do not know, but I will fix this one, then t minus z prime by c must be greater than 0, okay, which also means that z prime must be less than c into t. Okay. So, on the wire you have one influence, that is at z equal to a, okay, which actually propagates down towards the origin, and at the upper end will be this one, okay, which would be c capital T. Okay. So, there is a big sphere, you can imagine. This is the region which will be visible to me at z equal to 0 at a time capital T. Okay. So, instead of taking capital T, you can just take the small t itself, and of course consider the condition that t is greater than a by c. So, you can rewrite, go back to the integral out there. So, you had a mu naught by 4 pi which was constant, so I am just pulling this out, and then you had I naught which was also constant, so I pull that also outside, and the unit step function will now, or the limits of z integral will go from z equal to a to z equal to ct. So, this is c and small t. So, for any time t, okay, and this would be equal to, or rather this would be dz prime divided by z, but this integral can be easily evaluated. Dz prime by z is actually log of z, okay, in the limits of a and ct. Therefore, the magnetic vector potential A at z equal to 0 for all time t, only when t is greater than a by c, will actually be given by mu naught I naught by 4 pi log of ct by a along z axis. Okay. If you do not want to specify t greater than a by c, you can always rewrite this right hand side and then multiply it by t minus a by c, so that this step function starts at t equal to a by c, and thereafter it goes on. Okay. So, this is some rather interesting example that we looked at. So, when you evaluate these line integrals, you should be careful of what limits to consider. Okay. So, we will stop at this point because we would like to get started by finding the fields of the short current element or the elementary dipole, and we have now all the mechanisms available to us. So, we have all the tools that are available to us, which will allow us to find out the radiation fields for the elementary dipole. But before we do that, I would suggest that you go back to the expressions of spherical coordinates, of the expressions of curl, curl of the field quantities in the spherical coordinates, and practice a few exercises out there. Okay, because the computations get nasty, but we will be looking at what physical conditions finally would prevail upon and what is the physical significance of the fields. But most of the computations are very tedious because of the spherical coordinates and lot of differentiation that is involved. Thank you very much.